In this video, we're going to train a neural network to learn the sine function in Julia, including all the necessary steps like initialization, the forward pass, and importantly, the backward pass. Let's get started. Hi and welcome to this new video. Neural networks and deep learning are all over. These class of machine learning models have impressive abilities to capture any kind of function. And in this video, we want to look at a really simple case of a one-dimensional function learning, and we will put a particular focus on the backpropagation and the backward pass, because I think that this is something that is often overlooked, but it's yet the most beautiful aspect of neural network training, and we will see the backpropagation, as it is typically taught, is just a special case of reverse mode automatic differentiation. For this script, I want to make the following simplifications. We will not be too careful about train validation or test split. There will be no regularization on the network. We will do no stochastic mini-batching, so we'll process the entire dataset at once. We will also use plain gradient descent with a constant learning rate and no other training modifications. Our dataset will consist of n samples, for which we have an input and a corresponding output y, which was given by evaluating the sine function and adding some noise. We will reshape these data points into matrices. Input matrix X shall be 1 by n dimensional, and the output matrix shall be also 1 by n dimensional. So we will have one spatial dimension and n batch dimension. Notice that Julia uses the convention that the batch dimension is last. If you used Python, for instance, this would be opposite. Then we will prescribe a certain amount of layers. We can then use that in order to introduce weight matrices and biases that have the correct shape. We will see that in a second. And as the activation function, we will use the sigmoid, which is given here. The sigmoid has an interesting property in that its derivative can be given by the output from the primal computation multiplied by 1 minus the output of the primal computation. Then for neural networks, we have four major aspects. We have a forward pass, which is the evaluation of a network given parameters and an input. Then we will have an initialization stage where we will assign the weight matrices and biases with initial values. Then we also have a backward pass, which is extremely beautiful and allows us to obtain derivative information of a scalar loss with respect to all the parameters at once. And this will be a special case of reverse mode automatic differentiation. And then afterwards, we will have our training loop in order to adapt the parameters with the gradients. Let's go first over the theory of the forward pass. The forward pass works as following. So we have our input X, and take a weight matrix associated with the transition from the input layer to the first hidden layer, and I want to call this W1. And then we perform a matrix vector multiplication, or more precisely a matrix-matrix multiplication, because we are multiplying over the spatial dimension. And here you see if X is a matrix which is spatial by batch dimension, then we will retain that batch dimension in the columns. I want to call that output y1 here. Then we will take y1, which will be another matrix, which will be of the shape hidden size in hidden layer 1 with the batch dimension in the columns, and then we will broadcastedly add the bias, which will be a vector to each of the columns in our matrix. And finally, we will get our activated state at the end of the first hidden layer by calling our activation function, the sigmoid, element-wise on each of the entries in our matrix. And I want to indicate these broadcasting operations with a dot here, which also follows the convention in Julia. The next layer then takes this activated state from the first hidden layer and does something similar than this first transition. It takes our weight matrix, puts it into state y2, then batchly adds the bias, and finally applies the activation function. The third layer is the same, and the fourth layer is also almost the same, with the only difference that there is no true activation function, but the identity called here. So we will just say that the activated state at the end of our very last layer, you might even call it the output layer, is just given as the value with the plus bias. So there is no mapping in a certain range as your sigmoid function would do. As a last step, which is not technically part of a forward pass, we compute a loss value. Since we are in a supervised learning scenario, we have reference data for each of the outputs, and we can compare an element-wise difference. You might even put a point here in order to indicate we element-wise subtract the guess value from the reference, and then we perform an L2 loss, or a least squares loss in the spatial dimension, which is also multiplied with 0.5 here for mathematical convenience. Finally, we will then perform a mean operation over the batch in order to comply with the expectation which we are actually computing here. That is the forward pass. How do we start with our weights? And initialization for neural networks is crucial. As with any kind of optimization problem, you need to have a good starting point for your optimization. And this is a starting point in the parameter space of the neural network. This task is called weight initialization. And here we will rely on a technique that is called Glorot or Xavier initialization. And we do so by taking the weight matrices in each layer, here indicated with index I, and then initialize each of its entries independently of each other from a uniform distribution set between a limit or minus a limit and plus a limit, and the limit being given by the map in dimensionality. This is also often called the fan in, the fan out, so the dimension which the matrix takes in and what it produces. We will initialize the bias to be 0. Now let's go to the backward pass, which I think is the most important aspect for neural networks, as it allows us to obtain a gradient estimate independent of the number of parameters. And it works like this. So first we perform a forward pass and save all activated layer states. So we will save y1 activated, y2 activated, y3 activated, and y4 activated. And then we perform a backward pass. So we proceed in reverse order to the forward pass and do some clever computations in order to obtain our gradient estimate. And as such, it is just a special case of reverse mode automatic differentiation, which can be applied to any kind of computation. So here we are just limiting ourselves to neural network architectures, but this is a strategy that is found in many disciplines in science, often called adjoint methods or also algorithmic differentiation, and it has this really beautiful property. How does it work? So we will start with a cotangent information on our loss. Whenever I say cotangent, you can also think of it as the loss being derived with respect to this quantity. So if I, for instance, say the cotangent on y3 plus bias, this is loss with respect to y3 plus bias. So we will start with a cotangent on the loss. If you derive the loss with respect to the loss, it will give you the value 1.0. And this is a common start for those reverse mode automatic differentiation engines, since we have a scalar loss. Okay, then first have to pull back or backpropagate into our cotangent y4 activated state. And for this, we need the pullback rule over a meaned L2 loss. And in our case, this will give us the cotangent on the loss element-wise multiplied with the difference. So the difference given by y4 activated minus y, or more precisely the element-wise difference. And then we will also need to divide by the number of samples, because in the forward pass we perform the mean. So this will give us the y4 activated cotangent state. Then how do we go back to the y4 plus bias? And for this we need to backprop over the activation function, or the element-wise applied activation function. Luckily for us, the pullback rule over the identity function is not altering the solution, like multiplying with 1 here. So you could also just not do it. And then we have an interesting addition. So we have a matrix here, y4, and we column-wise add a vector b4. How do we backpropagate back into the parameter space? So we need a cotangent on the bias vector. And this is just given by the summation over the batch of the cotangents on the y4 plus bias. And that is because our b4 in the forward pass is kind of scattered or distributed to all of the columns. So we will get cotangent contributions from all of the columns, and this is done by summation. Then we also make the interesting observation that if we had a general addition, then cotangents would just easily backpropagate. There's no modification of them. And as such, we see that the cotangent on the y4 state is just equal to the cotangent on the y4 plus bias. Then we have our first transition. So we need to also go to the cotangent state on y3 activated. And here we will need the transpose primal matrix. So we will take the w4 that we also had here, transpose it, so we mirror it, and then matrix multiply with dy4, so the cotangent on the y4 state, and that gives us the y3 activated cotangent. But we shouldn't forget, we also need a pullback into the parameter space, so into dw4. And how is that done? In that we take the cotangent on the y4 state, which we have here, and then make an outer product with the y3 activated state. And this is one of the reasons I said we needed to save the y3 activated. So this is the y3 activated from here. Okay, now we have a gradient on the 4 matrix or a cotangent. Then let's go on to the next layer. And here we have to also get our cotangent y3 plus bias. But here we do not have an identity activation function, but we have the sigmoid. So we will take the dy3 activated, which we have from the previous layer, and then multiply it with the derivative of the sigmoid. And now we can make usage of this beautiful property that I wrote down here, in that we take the activated state y3 again, because we have saved it, and then element-wise multiply it with 1 minus of it, and then element-wise multiply it with that. And that's beautiful. That's how we backpropagate over the sigmoid function, or even more complicated, over the element-wise application of the sigmoid function. And then from there on, it's mostly the same. We will get a cotangent on the bias, a cotangent on y3, on y2 activated, on the weight matrix, and so on and so forth. We go all the way down to our very first layer. And here I put something in brackets, which is, we could also get a cotangent on the input. Oftentimes this is not really relevant, but more generally speaking, in the context of automatic differentiation, also in the application of recurrent neural networks, you might then want to do something with the cotangent on dx. There can be an application for this, but for us here, it is not needed, so I just put this in brackets. Nevertheless, we need the x again, because the x is relevant in order to build the cotangent on the very first matrix. And you might also see here, I have some of the pullback rules indented, and the indented ones are mappings from layer states back into the parameter space. These are the essential ingredients because they allow us to get the gradient, whereas all the other computations are just backpropagated within the network and not into the parameter space. So this is the third major ingredient. So the last one is probably the simplest, which is wrapping it all together and making it learn, or in other words, a mathematician might say, solve an optimization problem. So the very first step is we will initialize the weights because we need a starting point. Then number 2, we will run forward and backward pass. As said here, we will do it for all samples together. Typically, you would do some mini batching, but for us here, we are fine with doing it all together. And then we get both a loss estimate and a gradient. That is really essential. Then we will use the gradient. Here I called it a cotangent, but let's just think of it as a gradient. In a simple gradient descent step, we will take all the parameters. So here, for example, I have it for W1, and then update it by going into the negative gradient direction for a certain learning rate, typically called eta. And this is just a process we repeat over and over until our loss is sufficiently decreased. Okay, and since this video should focus especially on the backward pass, I want to give a little bit more detail. Essentially what we need are 6 different pullback rules. We need to pull back from the loss cotangent to the guess cotangent. Then we need to pull back over a broadcasted function application. We need to pull back over a batch broadcast vector addition. We need to pull back over general addition, matrix vector products, or more generally matrix products. We need them both in a sense of going from input to output, but also into the parameter space. So if you want more details, I have YouTube videos created for all the pullbacks here that are relevant in deriving them and discussing their properties. You will find the videos linked here. So take a look at the script. It is over on the GitHub repo of the channel. You can download it there, play around with it, and also take a look at these videos. So long story short, with this extremely long introduction, let's finally start with our implementation. And for this, I want to bring up a terminal shell here because we're going to work interactively with the Julia REPL session, which I think is really cool, so we can immediately see what is going on. So then let's first start with our inputs. Let's say we need plots, so because we want to visualize things. Here I already executed this import statement with a shift enter. Then we also need random for the random packages. Then we also need a distributions package for the initialization we're going to do with the uniform distributions. So then let's define some hyperparameters for reproducibility. Let's set the seed to 42, and let's say we will train on 200 samples. And then let's define our neural network by its layers. So it will start with a 1 layer, just the input layer, 1 spatial dimension. Then we have n neurons in our first hidden layer, another 10 in the next, then 10 another one, and then 1 in our final output layer. Let's set the learning rate to 0.1, and we will later on, during our learning, we will do 30,000 epochs. I mean, epochs is a little bit of an overstatement since we don't do mini badging, so this is just the optimization iterations. Okay, then let's start by first defining our random number generator, and I want to use the Mersenne twister from the random package, and then I will enter the seed here. Then let's draw some data, and I want to call this the x samples, and for this we will just use uniformly distributed numbers. So we will do the rand command, then we will provide the random number generator, and then let's say from which distribution. So we want to draw from a uniform distribution that is between 0 and 2 times pi. And from this distribution, we want to draw 1 times n sample values. And recall, this was because of the convention in Julia that we have spatial times x. And I also want to note this down, that Julia has the column major convention. And this basically means we have spatial times batch. And also just for all the Python viewers, so instead of the batch times spatial, you commonly see Python, maybe also in C++. Let's get our y samples. So we do some artificial data here just for simplicity. So y samples shall be the sine function element-wise applied to the x samples, and then we will element-wise add some noise by taking the random number generator again into the rand function, and then let's draw from the normal distribution with a mean of 0 and a standard deviation of 0.3. And here I also want to draw 1 by n samples independent values to make each of the samples individually noisy. So then let's take a first look at our data. So let's use a scatter plot on the x samples and the y samples and say that this is the data. So if we, first of course, we need our shift enter here, shift enter, shift enter, shift enter, on and so forth. We then also see if we made any errors. This kind of gives us immediate feedback. Seems good so far. Then let's do shift enter here as well. This will take a while because the plots package needs some recompilation here in Julia 1.7, but it will turn out that it will not plot anything meaningful, first insight, because we are trying to plot from matrices, which it kind of interprets as some batch plotting. So let's see what it brings up. So here we go. So we have scatter plots, but obviously it considers each of the samples individually. So I will just add the colon index here, which flattens the matrix into a vector. And then we should get a better plot. So you see it, that's our data. It follows the sine function, but it definitely has some noise to it. This is also a good point to remind you of that we are not doing here a train validation test split. So let's say the data we learn on for now, no train validation test split. So we will just inspect the hit or the result of the neural network visually. I mean, of course, for anything more sophisticated, you of course should do that. Let me make this a little bit smaller. And then we're good to go. So this is the scatter plot. So then let's define the sigmoid function to also have that at hand. So the sigmoid of x will be a function which is given by 1.0 divided by 1.0 minus the exponential of minus x. Oh, sorry, it should be plus. And then shift enters registers this function. Then let's create some lists. So we have the list for the weight matrices, which has the weight matrices for each layer transition. So we will have as many weight matrices as we have layers minus 1, because for 5 layers, including 1 input and 1 output layer, we have 4 layer transitions for which we want to define these matrices. Then we have our bias vectors, which will also be a list. And then let's also collect the activation functions in a list. Now, before we do the forward pass, I want to initialize the weights, just that we already have the starting point and can get some initial guess from a network. Let's start with that, the parameter initialization. So for this, I want to do some clever looping. So I want to say for fan in and fan out in a zipped iterator, where the first iterator is going to be the layers indexed from the beginning all the way to the end minus 1, and then the layers indexed from the second point all the way to the end. So we kind of get an iteration for these transitions between the layers. Then I want to calculate the kernel matrix uniform limit. So essentially, this was the limit we will then use in our uniform distribution. So this is the square root of 6 divided by fan in plus fan out. And then we can do our Glorot or the Xavier in uniform initialize. And this will give us the weight matrix W, which is drawn randomly using our random number generator from the uniform distribution between minus the kernel matrix uniform limit and plus kernel matrix uniform limit. And then we need to say how many numbers we want to draw. And of course, our matrix has to be of the shape fan out by fan in, because we will then later on matrix multiply it with the current state. So see here in the forward pass, we will have W1 times X. So the column dimension must be the fan in dimension. the row dimension must be the fan out dimension. And again, reminder, this might be different in different conventions and different languages. Okay, let's go down. This is our W matrix. Then let's say we have the 0 bias initialization. So B is just a 0 vector filled with the shape fan out. And then we push entries. So we append them to our list. So we push into the weight matrices list. We will push the W matrix. Then we will push into the bias vectors list, our bias vector. And I also want to push the activation function, and here I want to push the sigmoid. Let's end the for loop, and this is our initialization. So if we go up and do shift enter, shift enter, shift enter, and then run that here, and there we see layers, we made some issues, and of course we defined that to be capitalized, and so this should be layers, and here it should also be layers, and shift enter, here we go. Now we have that initialized. So for instance, if we look at the weight matrices list, we will get that this is a vector with matrices. So it has some matrices here. They are of course of different shape because we are mapping in the dimensionalities. And then of course we have to adapt a little bit in the activation functions list. So the very last activation function shall be the identity function. And here the identity function is just a default function in Julia. Okay, also let me note this down. The last layer is not activated. Let's go on and implement our forward pass. So function forward pass. So this shall be a function which takes an input x and then also gets weights, biases, and activations. So this shall be given some lists here. Okay, then we first say the first layer input, and let's define the current layer state with a and say a is x. Then we iterate over weights, biases, and activations, as those help us to transition between layers. So we will do for W, B, and the activation in zip of weights, biases, and activations. So there's the plural here. And then what we do is we will get our unactivated state. I just want to call that as set by doing matrix multiplied with the input and batch-wise added with the bias vector. So this is essentially the combination of these two operations. The reason I considered them separately here in the forward pass, because that later on helps us to unclutter what is going on in the backward pass. But here for our forward pass, we can use them together in one operation. And then we will get the next layer state, and I just want to override that by calling the activation function element-wise on this output set. Then let's end the for loop, and we can return a. Then end and shift enter registers that function. Let's use the same scatter plot and plot an initial prediction into that scatter plot. So let's have scatter and then use the exclamation mark in order to say we want to plot into the same figure. So what we're going to plot is examples, and again recall we need this colon here in order to flatten this into a vector. Then we call the forward pass. Maybe it's also nicer to call it network forward, maybe. So let's call this network forward instead. And then this can be called network forward here. Might be a bit nicer. So let's call the network forward on the examples with the initial weight matrices, the initial bias vectors, and the initial activation functions. And of course here we also need this colon indexing again to flatten that into a vector. And then let's also give that a label and say this is the initial hit. So shift enter, go, take some time, and there we have it. So let's make it larger. We now see that there is a prediction in, and yeah, it's not really nice. But the good thing is, due to the clever initialization we did, the magnitude is at least correct. So the prediction the network does is not really crazy. So that's a good starting point for our optimization. And later on, we will see that the network is able to fit this curve of the sine. Let me make that smaller again. Then let's go on and define the forward loss or the loss computation. And let's say function loss forward, which takes a prediction as well as a reference. And then what it does, it computes the delta, so the difference between, which is y, element-wise subtracted, y ref. And then we obtain the loss in that we take 0.5 times the mean over the sum of delta element-wise raised to the power of 2. And then we have to make sure, so we sum over dimension 1. So we sum over the spatial dimension, but we mean over the batch dimension. And then we can return the loss. This is our loss forward. Let's take a look. What does it compute? So let's call the loss forward on the network forward on X samples, weight matrices, bias vectors, and activation functions. And the reference, or maybe I should put that into a new line. And the reference shall be, of course, the Y samples we drawn earlier. And then Shift Enter gives us a loss value. So we are at 0.37. Here we don't contract fully into a scalar, so this is a little bit ugly to look at. So let's just take the first entry from that matrix in order to get a scalar here. Okay, now comes the critical part, the forward and backward pass. This is the beauty of neural networks, how they obtain their gradient estimates. Okay, so let's start with a function and call this network forward and backward, because we want to have that in one function. This should take an X, a Y reference. It should take weights, biases, activations, as well as activations derivatives. We will see that in a second what that means. And then what does it first? So again, recall, how does this backward pass work? The first step is to run the original forward pass, but save all activated layer states. So this is in contrast to the forward pass we implemented, because here we overrode the activated state or the layer state, because we don't need it, we can throw it away. But now we need to save it. So let's start with that and say again, similar to before, the first layer is the input. So A is X, and then we also need to store the intermediate activated states for the backward pass. And for this, let us create a list and say these are the layer values. And let's start with A there. So we'll also save the input here. This is just for convenience later on. And then we do almost the same as we did in the forward pass. We say for W, B, and the activation in zip of weights, biases, and activations. We will compute Z by taking W, matrix multiplied with A, and then element-wise added with the bias vector B. Then we will say A is the activation function, element-wise called on Z. And now with the difference that we push this onto our layer values stack, you might say. So layer values and push A, and then end the for loop. And then, of course, the very last layer state, which just had the identity activation, is the output. So Y is A. And then we can compute our loss by taking loss forward and say Y and Y reference. So this is just that we also return the loss. It helps us assess the fit of the model or how far it is in our optimization. And then we can start the backward pass. So the very first thing we need to obtain is the Y cotangent, so the cotangent on the very last layer state. So this I want to implement in a separate function, and I want to call this the loss backward, which takes Y and Y reference. And then recall, how does it compute that? So in the backward pass, it says that the cotangent on Y4 activated is the cotangent on the loss. So it's 1.0, so we will just ignore it here. And then it is the actual delta from before, but element-wise divided by n, because we did the mean in the forward pass. So let's go down here and say we first compute the delta by being Y element-wise subtracted with Y reference, and then let's obtain the number of samples by looking at the size of Y in the second dimension, and then we can return delta divided by n, and that's our current cotangent. Shift Enter also registers this function, and then we can get the current cotangent by saying loss backward on Y and Y reference. Now, before we do our reverse loop, we also need a way in order to save the gradients for the weight matrices and the biases. That's the actual intention on why we want to do the backward pass, because we want to obtain these gradient estimates. So let's say weights gradients is a list and bias gradients is a list. Now we have to go reversely. So we will do for W activation prime. We'll see in a second what that is. activation prime, a current and a previous in zip. And then what do we have to iterate? So we have to reversely iterate over the weights. We have to reversely iterate over the activation derivatives. We have to reversely iterate. Okay, how do we get the current? In that we say that layer values indexed from 2 to end. And by current, I mean thinking in forward sense. So it is the current we're currently at. And the previous is obtained by layer values starting from 1 to n minus 1. Why do we need both the current and the previous? So if you look at the backward pass here, we saw that within one layer computation, you both need the y2 activated as well as the y3 activated. So we need the y3 activated in order to go from the cotangent on the activated state to the cotangent on the plus bias state. And then we need the y2 activated from the previous layer to say, in order to get our cotangent on the weight matrix. So this is crucial here. We go down again. And now let's do our computation. So let's take our current cotangent, which is the cotangent on the activated state. So let me do this. This is the activated state cotangent. So this is basically what we get from the subsequent layers which we already backpropagated from, and in the start it will just be the loss backward. And then we get the plus bias state cotangent by taking the activated state cotangent, element-wise multiply it with the activation prime function, element-wise called on the A current. This is using the properties from the sigmoid. So the sigmoid is given that its derivative can be expressed in its primal computation. So we will hand over the primal computation, and this activation prime will then compute us this sigmoid prime. That's what is happening here. So we get the plus bias state cotangent. Then we will get our bias gradient by summing the plus bias state cotangent on the second dimension, so over the batch dimension. So summation over batch dimension. And recall, we needed to do that because in the forward pass, the bias is scattered to all the columns. So we need to kind of gather the information from the scattering. Then we can also get the state cotangent. So the state cotangent, and we saw that this was nothing else than the plus bias cotangent. It's because the pullback rule for addition is relatively straightforward. Then we can get our weight gradient, also call it the weight cotangent, as, and this is a crucial point, we take the state cotangent and multiply it with a previous. And therefore we needed both a current and a previous, but we have to be careful. We need an apostrophe here in order to denote the adjoint to get the outer product. And then we can also get the previous activated state cotangent by taking the weight matrix, transposing it or adjointing it with the apostrophe here, and then matrix multiplying it with the state cotangent. And here we see we now used all the 4 iterates here. We needed the A current in order to get back into the plus bias state. Then we needed the activation prime as well here. Then we needed the A previous in order to get our weight gradient. And we also needed the weight matrix in order to get back into the previous layer. And it's because the weight matrices are always as the transition between layers. They are mapping the dimensions. Okay, then let's push into our list. So the weights gradient goes into the weights gradients, obviously. So weight grad goes into weights gradients. And then into the bias gradients goes the bias grad. And then in order to finalize our pullback over the layer, you will say that the current cotangent is the previous activated state cotangent in order to get our causality right. Let's end the for loop. And this is the backward pass. So what does the overall function network forward and backward now return? So it shall return the loss. And then it shall return the gradients on both weights and biases. They are still in a reverse order because we iterated reversely. So let's just reverse them again. So the reverse on the weights matrix, not on the weight matrices, but on the weights gradients. And then the reverse on the bias gradients. Let's end that here. So shift enter registers this function. Before we can make a sample call for it, we first have to define the sigmoid prime. But we don't want to define that it takes its primal input, but it should take its primal output. So it will get an activated state, and then we know it will give us the derivative by getting the activated state, multiplying it with 1 minus the activated state. Okay, let's shift enter to register this function, and then let's have the same for the identity prime, which will be given some x activated, but it just returns 1 because that's what it does. Okay, then let's collect this into the activations derivatives. We take sigmoid prime and just get a list for this by saying for some iterator in 1 to length of layers minus 2, and we will just unroll this and add an identity prime. This is a little bit fishy here. Oh, of course we need the identity prime, so it's a little bit not too verbose here, but essentially this gives us a collection of 3 sigmoid primes and identity primes, and if you were to change the number of layers, it would adapt for that. Okay, so far so good. Let's give us an initial call for the function, this network forward and backward, and say we have an initial loss, we have an initial weight gradient, we have initial bias gradient, and for this we will call network forward and backward on the x samples, on the y samples, on the weight matrices, on the bias vectors, on the activation functions, and on the activation derivatives. Here we go. And let's see if that works, if any mistakes. Okay, it runs through. Does not mean it's correct, but at least that's a good sign. So we will have an initial loss. Okay, yeah, I made a typo here. Let me fix this and enter this again. So initial loss. Okay, here we go. And this is identical to if we just called the loss forward. So it gives us the same result. I mean, we essentially did the same with the only difference of saving the intermediate states. Then how does it look for the initial weight gradients? So this will be something which has the same shape as our weight matrices. So weight matrices. And so therefore we can like element-wise update that. Okay, that's great. Works so fine. Let's see if that is also correct by implementing our training loop. So this will be another for loop, and I just want to save the loss in each epoch or in each iteration. So let's create a loss history list and then do a for loop for the epoch in 1 to number of epochs. And then we do the forward and backward pass. So we will get loss, weight creds, we will get bias creds, and call network forward and backward. And here, this will be on X samples, on Y samples, so this will never change. Then we have the weight matrices, they will update. We have the bias vectors, they will also update. Then we have the activation functions, they will not update. And then we have the activation derivatives. Obviously, they will also not. Okay, this gives us the loss and the gradients. So now we have to update. For this, let us again use some clever zipping here. So let's say for W and W cred, as well as B and thread in zip of weight matrices, weight gradients, bias vectors, and bias gradients. And then essentially what we do is we say that we update W with dot minus equal. So we will override the value by element-wise subtracting the learning rate element-wise multiplied with the gradient. Something similar for the bias vector, so dot minus equal learning rate element-wise multiplied with the bias gradient. And the for loop, this is our update. And then let's do some nice printout. So we do 30,000 epochs. Let's do not print out in every epoch. So let's say if the epoch is divisible by 100, that is equal to 0, then we should print out some information and say we are currently in epoch. So we will use some string interpolation here, and we are having the loss according to loss. And then we will also push with the loss history with the loss value and then end that. Now we have the moment of truth. Does it work? Let's do shift enter. And of course, yeah, I did not shift enter on the list here. Let's run that. Okay, the loss seems to be decreasing, but oh, that's not running well. Yeah, we might have had a small mistake. So I played around with it a bit, and it seems that we might have had some wrong shift enters at a certain point. So there's no difference from my reference I have here. So let's just go all the way to the top and re-execute that. And let's say shift enter all the way down. So you can just continue hitting the shift enter. So you will again get our initial fit, and we'll also get a loss. Interestingly, we will have a different loss. I don't know why it is different. I must have made some small mistake there. Probably I will add a little notation here on what was wrong, and I will leave something in the comment section. Okay, anyways, let's go on, and with shift enter we work our way all the way down until the final training loop, and here finally the loss is decreasing as I wanted it to. So we will have a strong decrease in the beginning, then it's getting less over time, and we will do our 30,000 epochs here. So now we're done. Okay, so let's make a prediction plot how our network would position the training samples. As said, that is relatively stupid because we did not do any train test validation here, but we have a good feeling that our network learned the sine function. So let's do a scatter and again exclamation mark on the X samples and the network forward called on X samples weight matrices. These are the updated, the learned weight matrices, the bias vectors, as well as the activation functions. And don't forget the colon in both. And here we go. Yes, so then you can shift enter. And here we see our network learned the sine function. Isn't that beautiful? I mean, it did not fully get the magnitude right. So here it is at 1.0, but there it did not. So this is probably where one has to tweak that further, but it's still a good learning result, I would say. Finally, let's make a plot of our loss history. So here we go. And this is the loss history. Basically what our network learned. So we started with initial loss around 0.33 and then got all the way down. So it's probably even nicer to look at if we do that in a log scale. So y scale equals logarithmic 10. And here we go. So it started, it decreased it by about an order of magnitude. So here it had a small hiccup, but then it continued decreasing the loss. So let me quickly summarize the video here. So essentially what we did are the implementation of the 4 major steps in a neural network. The forward pass, so the evaluation of a network, and crucially, there we did not save anything, we just threw away the states, continued our computation. A weight initialization to give a good starting point. So this was, if I go back to the plot, this was basically the orange fit here. So it is a good initialization because it does not have a stupid magnitude and it also does not do anything stupid. So it's a good starting point for the optimization problem. Then we had the backward pass, which is always combined with a forward pass. As with automatic differentiation, you will always need a primal evaluation of your function. And this allowed us to obtain gradients, and that we used for gradient descent, which is our learning or training loop. And we did about 30,000 epochs. The loss decreased to an extent where we at least happy, and we got a network fit. Also stay tuned for the next video where I will show you how to create a simple animation in Julia that lets us see how the network learns the sine function. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There is more awesome content on deep learning, neural networks, but also how all of that interplays with physical simulations. So there is a lot of cool videos to watch. Here you will now see similar videos, and I hope to see you in one of the next videos.